Okay, so let's start. So just have a look. Okay, we go on with the next chapter, which is one of the chapters will be in your quizzes. Okay, so this we call as inductor. So this chapter is actually related to your magnetic field. Okay, is why because we only can have we can show the magnetic fields works based on the motions or based on the directions. Okay, even we can feel the magnetic fields. Okay, usually happens in the inductors. So inductors means is like a we call as a component or we say it as a element, okay, and same as like a capacitor, it seems like a resistance, like other components, okay, and this is one of the electronic components where we call as an inductor or inductance. So let's go with the next slides here. Okay, in the next slides, you may have a look. This shows you in terms of figure here. Okay, is where they have a coil turns here, and where they shows you in terms of terminals. Okay, it's where these two terminal, this terminal and this terminal, and these two terminal always we have need to have the polarity positive with the negative. Take note, your inductance always need to have a polarity positive with the negative. Okay, and based on this figure, what the component is it? Okay, even our slides also we already have the title is inductor. So of course, these components which is stand for inductor. And what they mean with the inductor? Okay, you may have a look where we call as a coil choker or we call as a deactor. Okay, when also at the same time we call as a passive two terminals electrical components at the store energy in a magnetic field. Okay, take note. At the same time, when Miss go through based on the capacitance, is where Miss also highlighted based on the stored energy. It's the same, but it's not exactly the same. This one they call as a stored energy in a magnetic field. Okay, it's an inductor. Okay, even when the electrical currents flow through it. Okay, and the inductor typically consists of an insulator wire wound into a coil around. Okay, which are around a um, which are around the core. Okay, so you may have a look what they mean when they call as the insulator wire. So insulator wire, as I inform you, always we have a conductor, we have a semiconductor. The third one will be insulator. Insulator means we can't have any current flow. We cannot have any voltage. So when we can't have any voltage, definitely we cannot have a current flow. Semiconductor, we still can have a current flow, but conductor is the best materials where we can have the current flow. So what they try to say based on the insulator wire means sometimes due to some protections of your to avoid a short pattern or to avoid the current flow in the same flow. Sometimes they separated the current flow in a different directions. That's the time we need to have cover up. Okay, we say we cover the copper with a different material. So that material that we're going to use right now is based on the insulator to cover up that. So even as Miss explained to you last time, okay, example, right now I have this cable, okay, this is a earphone cable. So inside here we have the copper, we have the jumper or we say as a wire, okay, but outside here you only can see as a white, okay, and this the one we call as an insulator. So when I touch, I don't feel anything, okay, but without this part, without the cover of this white, okay, it's something can happen, okay. So that's the reason we need to have covered with the proper insulator to, because we cannot feel the current flow, okay, it can be short back to us, all right. So that's the one they call as an insulator wire. It means based on the terminal. Okay, so let's go on with the next slide. Okay, in the next slides where we have based on the learning outcome, inductor is the same concept where we call as a magnetic field. Okay, so let's go on. In this part, okay, this is where the key words where we call as an inductor, at the same time they call it inductance, at the same time they call as a cell inductance. Okay, but they have a it's actually the same, but when you do some cell inductance, maybe the formulas they try to implement it, maybe they add or minus based on the parameters value. Okay, the next one based on the EMF, as we know, is based on the force. Okay, and the next one, okay, you may have a look on the same law where we have in inductor, where we call as a Faraday law. This is the one. Okay, so it's connected. So let's go on. And the overview of the inductors here right now is just a type of the inductor. Okay, and what is the inductance and the factor affecting it. Okay, so example, even for the capacitor, we have some factor affect the a capacitance based on the current flow or based on the voltage. Okay, so based on the circuit, right? So maybe can be based on the thermal. Thermal means the heat. Okay, so same goes to inductor. Inductors also, they have a few factor which we say will affect the value of inductance. Okay, maybe they can increase the value, okay, or based on the current flow. All right, that's the one they say the factor affecting based on the inductance. The next one is based on electrical characteristic. Okay, electrical characteristic means is randomly based on your equations calculations. Okay, at the same time, based on the characters, based on the issues, or based on your parameters, based on electrical field, how is it works connected with your inductance. So that's the one shortly they say electrical characteristic. The next one is based on inductance in series, parallel, and series parallel. So it looks like sounds similar which you when you did for your capacitance. Where in the capacitance also we have the series parallel and series parallel. It's the same thing for your inductor, but this time they're going to arrange your circuit diagram in terms of series parallel, but this time they're going to use the components as an inductor. Okay, the flow or the methods or the way arrangements of the circuit will be the same flow, but this time they're going to replace inductor as a component. Okay, and the next part based on the energy store, and also they call as a Q factor. Okay, so let's go on with the next slides here. Okay, this is not going to go on read everything based on your history of electromagnetic, but you can have a take your time and go through who's the finder, who is the founder of the inductions. Okay, so usually this we call as a scientist person who can come up with the equations, which come up with the theory, the basic theory, what they mean with the electromagnetic inductions. Okay, right now Miss also explained it to you in the previous class based on the flower, based on the magnetic. So each theories that we learn is from this person. Okay, and every time, okay, usually although we have the first person as a founder of the theory, we always have the person's improved the theory. Okay, so but usually when we say based on the magnetical inductions, this is the persons that we always have a look. Okay, and where if you see, we call as a Joseph Henry, and the units usually scientists when they try to come up with a new theory form or new formulas, they try to come on, they try to insert their name, okay, in your equations or in terms of theory. So if you see the one, just have a look here, due of the inductance, voltage, everything, they call as a Michael Faraday. At the same time, this one, I just want to highlight their names here, okay, Joseph based on the Henry. And when it's come to your inductions, the unit that we use for calculate your inductions is where in terms of Henry. So every time the scientists, the founders, they try to substitute their name, okay, in the theory part or in the equations part. Okay, so you can have a look based on the history. Those are willing to know more about the histories, you can try Google it. Okay, so let's go on direct to the point here right now. Okay. Okay, inductance is name is given to properties of the circuit wherever by there is an EMF. So EMF, inductance, magnetic flux, magnetic density, okay, flood density, and also what is it? Inductance, EMF, magnetic field, flood density at the same time. Based on your magnetic field strength, everything are related. Okay, make sure you need to know when it's come inductance, all the keywords let me say are related for the inductance. So from here, the information they given to you or the explanation they given to you based on your slides, okay, is where they say EMF, inductance into a circuit by the change of the flood leakage produced by a current change. So is one of the factors I can say is a current also. Okay, and the next one they say categorized as a cell inductance and mutual inductance. So in a inductance are the same for your cell inductance and mutual inductance, but they have a slightly they have different. Either they're going to add the value of parameters or they're going to minus the value of the parameters. So that's the one difference here. Okay, the way the equation they shows you the way they calculated. Okay, but usually there's the same thing. Okay, the next one you can see the unit they measure for inductance. Okay, we call as a Henry. Okay, at the same time, okay, before we go with the formulas here, I just want to show you a few things here. Just behold, or inductor. Okay, just have a look. Okay, this is how the inductor look like in your real life. Okay, so this is a they can come out, but usually your inductors, they have a coil, they round up, they circle or they turn up with a coils here. Okay, so just have a look. This is the one. Okay, that's why we say even we can design based on the transformer. At the same time, we also can design for the inductor. Okay, the way of the inductor. All right, because each of the inductors, they have their value. Okay, example capacitance, they have their value, right? Like I say, 2 microfarad, or we say 2 picofarad. The same goes to the inductor. Each of the turns, okay, or based on the design, have their value. Okay, so just have a look the examples here. This inductor indirectly related to your transformer design. Okay. Hmm. Okay. Just have a look. Just have a look on the pictures here. Just have a look on the pictures here. The way they have the design based on your inductance design. Okay, I think so far this we have here. Hmm. Okay, so example, just have a look this one. This they put in the top of PCB or your printed board. This one, okay. So this represent as an inductance value. The next one is should be your capacitance. Okay, so just the one I want to show to you all. Let's see whether I can find other types of inductors here. Okay, that's the one. Okay, just go back to your slides here. All right, the unit we call as entry here. Okay, so let's go on with the next part here. So EMF, which is related to the law. Okay, so this law we call as a Faraday law. And where how they come up with the equations here. Faraday law is the inductance EMF is given. So it means they have an equation to be calculated. And these equations we are going to stand as a V. Okay, equal to N times with the rate of the changes of the flux. So have a look the way they calculated based on the induction. So this time they take note based on the turns. At the same time, they have a look the rate changes. This time they not exactly take the value of the flux, okay, magnetic flux, but they have a look the rate of the changes happen on the flux, magnetic flux. So when you have a look on the equation, this equation this shows you in terms of your maths. I think you have go through a differentiate. Okay, differentiate the plus with the dt. Okay, so this is a one of the formulas they shows you in terms of the maths, the way they calculate it in terms of the max. Okay, all right, so have a look on this next one. Okay, just some explanations you can have a look. Okay, it's just a notes. Okay, how they come out with the based on the science. Okay, now you just have a look on the parts here based on the calculations. So in this calculation, just have a look. So if the flux through a 200 turns coil changes steadily, okay, from 1 WB to 4 WB, okay, it's 1 second. So they highlighted for us the time, at the same time they highlighted to us based on the coil turns, okay, based on the flux here. And what's the voltage they assigned it to you? We need to know the voltage, okay, inductance, how much is it to work. Induct, okay, based on the diagram, this circuit. Okay, example, we just assume we have a circuit here. And the way they calculated to define the value, okay, is where you need to find the changes of they specific the changes is how much in this part. So it means they're not going to highlight it to you directly the value changes happen, but you need to trace the way from the question they given to you, because they already highlighted to us the changes steadily, okay, steadily from 1 to 4. So from here you need to know the changes happen. Okay, sometimes they can give you a difference value. So from here, of course, when we say 4 minus with your 1, okay, to get the value you need to know the value is how much the flux density changes. So from there you can trace it stand for your 3 WB in a 1 second. Okay, is related to your 1 second. So from there you can identify the rate of the changes based on the time. Okay, based on the velocity, based on the speed. Okay, we just say based on the time. Okay, which is stand for the 3 WB per second. So that's why they put a slash s. After that, easy for you to calculate to define how much the voltage, okay, how much the voltage inductance based on your equations here. Okay, your flow of the equation. So you just substitute based on your, you have 200 turns, substitute in the equations, you have 200 turns times with the changes of the time. Okay, how much is it? Sorry, not changes of the time, the changes of your flux. How much is it? So it's a 3. Okay, but take note based on your speed, based on your time too. per second. They already informed it to you based on the second, 1 second. So per second means is 1 second, equal to 600 volt. So this from here you can identify how much the voltage inducted to your circuit. Okay, so take note, the one they write is just the changes, the difference happens between the flux, between the time. Okay, and some of the reference book they use the word E. Take note, even in the first time we go through based on the equation, some of the they call as energy, but they highlighted as an E. But actually the E are represent for the voltage. So to ignore a confuse, okay, you can stick with the T. Just define it as a V, which is stand for volt. But I just want to highlight it. Some of the reference they just specific as a E. Okay, it's the same thing based on the word. Okay, let's go on with the next part here. Okay, next part also is represent some equation, how they calculated based on the equations here. So this is one of the equations they take note based on their terms, and also based on the length here, based on the inductance. Sorry, this is not length, it's based on the inductance value. So it's where they have the changes of the flux at the same time related to your time. The next one, they have a two. Take note, they have two equations. Just take note, maybe you will understand when you try to do a calculations later on. Okay, the second one is based on the inductance. They given to you the value of the inductance is how much. At the same time, they let you know based on the current and also based on the time. Okay, defined it based on related to your voltage V. Okay, let's see they have any example. Okay, they don't have example. Okay, just go on with the next one, cell inductance. Okay, what the difference between inductance? What the difference with the cell inductance? Okay, when it's come to your cell inductance, okay, is where they're going to take note based on the inductance value. At the same time, you also can plot it the based on the volt that you're going to have based on your inductance. But at this part, you should say inductance times with the rate of the current. Okay, just now when we want to calculate for inductance, we take note based on the changes of the flux. But when it comes to your cell inductance, we're going to take the rate of changes of the currents. So the way they calculated at this time, you can see the way they calculated for your V. Okay, is where they're going to have the inductance L, and the same time they're going to take the value. I mean the differences value currents flow. Okay, at the same time they take note based on the time. So you just substitute based on your equations. Take note at the same time you also can have the turns of the how many coil turns that you have. Okay, when they ask you based on the turns, when they specific for you based on the flux, then you can define your equations in this form. Okay, and usually the basic formula for your inductance is the one. Take note, the basic formula for your inductance is Ni based on the flux divided by the current. These equations for your inductance equations. Take note about this one. Okay. Okay, the next one, let's have a look on the next part here, inductance formula. So in terms of the inductance formula, you have the formulas here where they have this the time they substitute based on the permittivity. Okay, let's have a look. In the earliest, you only had defined length, did not specific based on your permittivity, did not take note based on your what type of materials, that you're using for your the turns that you want going to design. Okay, but this time, the next part inductance formulas that you're going to have is you take note based on your permittivity. And this time, your formulas, you have a different changes based on your formula. Not different changes, is stick based on the information they given to you. So example, on your inductance here, they given to your permittivity. They also highlighted based on your turn, but this time they call power of 2. Okay, and where they multiple with it. A is means the area and also divide by the length. Okay, so most of the thing I just asked you to take note based on the permittivity value they given to you. As usual, we have the substitute the absolute value, we have the relative value. Alright, so in this part, they just let you know the first point here, your length stand for your meter, your A stand for your power, meter power of 2, your N stand for your length, as usual we know. And also this is a missing, actually this is the micro. Okay, micro is the permittivity of the core. This means the core, this one. Alright. And where they say based on your accuracy. Sometimes they calculate it based on your accuracy. Okay, how is it based on the magnetic field? They have some ratios in terms of the ratios calculations. So in terms of the ratios calculations, you can just define it based on the length with the D, ratios D, based on your diameter. Okay, and usually the concepts here, they let you know is greater than 10, they have an error, lesser the error than the 4%. Okay, This part we use to calculate based on your accuracy. Okay, most of the thing in the EP, we're not going to cover based on your accuracy calculations, but we always focus on the way how you calculated inductance, how you calculated your cell inductance. Okay, but this is your informations. Okay, and the next one, okay, this is just for information to you. To provide a great inductance in small space, iron core are sometimes is used. Okay, so sometimes when you want to start to design, you need to take note based on the diameter. Okay, sometimes it's exactly follow your materials. So the more thicker what happened to your current flow is most I mean here based on your circle. Your circle is it is more bigger, the diameter is more bigger or more smaller, because when you have the diameter of your cooper is more bigger, then you need indirectly the coil, the cooper that you're going to have, the long, the turns that you're going to have is more larger. Okay, so that's also will be affected based on your inductance value. Okay. Okay, that's all. And just have a look on your diagrams here. The way they calculated for your single layer coil, the equation is the same equation. You take note, it's the same equations. And the same time, they shows you in terms of the hair gap. Okay, just now we always have the inductor square in this form. Okay, it means we don't have any in terms of a diagram, we can't find the one with the gap, but this diagram you can see they shows you have the gap between this core. Okay, it's the same core, but they did some separations. Okay, you have some spacing. This is the one you have some spacing. Okay, is where why they have the spacing here to control the saturations. Okay, the flow, right? So just take note based on the equation that we have based on the inductance formula. Okay. Today we just go some theory part for your inductance. Okay, so I'm not going to cover everything, but just a few things that I want to cover up based on inductance. So the next class Miss will continue back. So for right now, we just skip the example as I let you know. We know just for theory part here. I have many calculations for it. Today just theory part. Okay, just have a look on the next slide. Okay, this slide you may have a look based on the inductance series and parallel. Okay, take note. The one is taught you in capacitance, the flow series and the parallel. Okay, the way they use the equation to calculate. Okay, when you see for your inductance, later you compare. I want you to compare the flow of the capacitance, the flow of the inductance, because later on you will learn based on the resistor. Okay, the flow of the resistor when it's series and parallel. Okay, so at this point later on I want you to compare. Okay, what is it when we have a capacitor in the series form? Okay, what will happen when we have an inductance in the series form, a parallel form? Okay, have a look on the equation. There have a difference based on the equation. Okay, let's go on with the figures that we have right now. So the first figure it means this one. Excuse me, the first figure one means this one, the second one means is this one. Okay, so the series 4.6 we call as a series. It's not a case, it's just a series in terms of the way they arrange the components in terms of the series. Okay, so they write for you L1, L2, L3, Ln. So Ln means can be multiple. Okay, maybe can be the L10, can be the L12, can be the L15. So it's where you need to calculate based on the total inductance. So when they highlight it to you based on the series and parallel circuit, usually you need to take note. Definitely they are going to ask you to calculate based on your total inductance. At the same time, they also can ask you to calculate based on the voltage. Okay, at the same time, they also can ask you to calculate based on the currents. Okay, but usually when it comes the forms of series parallel, take note, they always ask you to calculate the total of the inductance. So when it comes to the series, you may have a look. They ask you to calculate L1 plus L2 plus, okay, pluses, okay, until you go on with the Ln. So that's the one we say plus, plus, plus. Okay, now have a look on the figure 4.7. Okay, 4.7 we have in terms of parallel. Okay, just let you know, capacitors also series, we arrange the capacitor in series form, the same connection. When it's come to a parallel, we did in the opposite, okay, based in the shunt form. It's the same goes for inductance. It's the same thing, but the equations are different. If you see later on, I want you to compare. So in the parallel form, the way they calculated for your total inductance. So the way they calculated 1 over LT equal to 1 L1 plus L1. Okay, Okay, continue based on the equation. So this is the one we use to calculate the parallel circuit. Okay, so the next one based on the next part. Okay, this shows in terms of parallel. I think everyone will maybe some or everyone know the equation how they calculated for the parallel concept. You can go on with this one, this format. You also can go on with this equation. Now format, the way they calculated based on these equations, based on this equation. So let's go on with the next part. Okay, next also they given to you a calculation. So I'm not going to touch any calculations for this right now. Let's have a look on this part. Okay, this is where they calculated based on an energy store in inductor. Okay, it's where inductor posted by ability to store energy. The energy store where we calculated in terms of W. Okay, and where they have used a magnetic field on the inductors, the way they calculated the value. So just have a look on the way they calculated to define the energy store. Okay, in inductor. So these are the equations they're using 1/2 times with the Li. Okay, Li means the current power of 2. Okay, this actually is a unit. What's the unit for your energy? Okay, not work done, but we call it as the energy. How much is it? The unit in a joule. Alright, so this is the equation they implemented to calculate the energy store. Okay, let's go on with the next slide here. Okay, next also is the calculations. So I'm not going to touch any calculations for inductance part here. Okay, that's all. Okay, inductance is a very short, how to say, is a short chapters that we have for inductance, same like your capacitance. Okay, so since we have some more of 10 to 15 minutes, okay, so I just want to, not to test, just some feedback from you all. Take note, the next one will have some calculations based on the inductance. Okay, so I just want to go on some, not testing, just want to see whether you understand or not. Oh, this is a number. This is a magnetic field. Okay. We catch up during the tutorial. Right now, okay. Inductor. Okay. Okay, so please will type your name or I will call your name. So the person that I call, you can respond to me. Those means not going to call, then it's okay. You just keep your answers with you. All right. We have class later. Just give me 2 minutes. Let me sketch and write down. Okay. Okay, so everyone have a look on my screen right now. So you have 3 image right now. You have 3 figure. So the first one, you have 1 figure. The second one, you have 1 more figure. Okay, I hope you can see. And the third one, you have 1 more figure. So I'm going to call one of you right now. So those are listening to me, maybe they can answer. Okay. Okay, maybe I go with a volunteer, anyone. I'm not going to pick up. I'm not going to call the students, maybe volunteer anyone. Okay, so I'm not going to choose you all. Okay, I'm not going to call you, but is a volunteer. Anyone can answer. So the first one. Okay, so when you have a look on the first figure, what is it, the figure? What figure is it? Those shy to talk, maybe you can just write your answers in the meeting chat.
Series.
Series. What series is it?
In the inductance form.
Yeah.
Series in the inductance form.
Okay, all right. So those I can't remember. I can't trace. I can't identify your voice. Okay, recognize your voice. So thanks for your answer. Okay, when you have L1, L2, L. Okay, based on the figure, you have a few L's. Okay, what's the equation that we need to use in case I ask you to calculate the total inductance?
Use formula LT equals to L1 plus L2 plus L3 plus L4.
Okay, thanks for the answer. Okay, let's go on because Miss will come back with the number 1 again later on. So number 2, okay, can I know what circuit is it? I want anyone try, please be volunteer.
Parallel circuit,
Parallel circuit. Okay, what parallel?
inductance.
Okay, so thank you. Let's go on with the next one. Okay, what's the equation that you will use to calculate when they given to you this kind of circuit?
1/1 over L1 plus 1/over L2 plus 1/over L3 plus 1/over L4 plus 1/over
Okay.
L5.
Okay. So the one you say as a total one, do we have LT equal to 1 over L1 or they will have 1 over LT equal to 1 over L1. Which one?
LT equals 1 over L1
Okay.
plus 1 over L2 plus.
Okay, all right. Thank you for your answer. All right. Okay, the next one. What is it? Can anyone define for me what circuit is it? The third figure here.
Parallel and series circuit.
Okay, all right. Thank you. All right. So the next one, when example, I ask you to calculate the total of the inductance. I don't want you to calculate, but don't want for me based on the calculations part, but just labelly. Okay, labelly explain to me, verbally explain to me how will be calculated in case Miss asks you to calculate the total inductance for the third circuit. Okay, what are the things that we need to take note before we start to calculate the total inductance for your number 3? Anyone? It's okay if the answer is not right. Just try and error. Those not yet try, you may let me know your answer. What do you need to take note? Okay, when you want to calculate for the total inductance for number 3. Just now one of your friends already give you the evidence where he said this is a series parallel inductance circuit. Okay, so from there for you to identify the equations. Not exactly the equations, how the flow will be. What do you need to do? Okay, I get some response. All right. Must find the answer parallel circuit. Okay, that's from one of your friends' answer. The second one, split out. Okay. Anyone answer? Split out. Okay. Anyone answer? Okay. Since time is too short right now, okay, I just let you know. So when you want to find the total inductance for your number 3, take note, you need to simplify your circuit to find the total inductance. So that's the time that you need. Okay, some of you give me the answers here. Take note, okay, which is parallel, you do it for the parallel. After that, you need to simplify your circuit. Okay, it means you're going to have a look on this part. You're going to have a look on this part. Okay, at the same time, you're going to have a look on this part. Once you have a look on this part, you have some calculations on your inductance, you simplify your circuit. Simplify your circuit means you narrow down your circuit. Okay, from one point, a big, huge circuit, you simplify to the second one. So from the second one, you simplify, narrow down to the smallest one, okay, until you can find your circuit in this concept. Okay, it means you're only going to stand one inductance and maybe you have one more inductance from this view. Okay, maybe some only you have one inductance in this view. Okay, so at the end you simplify your diagram to this small inductance. Okay, it's similar how you did for your capacitance. Okay, the flow would be the same, just the formula will be different. Okay, and just want to ask a few questions here. Okay, what the definitions when Miss asked for you if I ask for inductance? Can anyone specific for me either key point or definitions in one sentence? What is the inductor? What is the inductance? Key point. Key point also okay, can. Definitions or the key point of the what they mean inductance. How they related. Which terms are related to inductance? Come up with your own words, your own sentence. Don't take from the slides. Okay. What your understanding based on the inductance? Definitions, key point. The key point that we need to have a look. Inductance.
inductance, I think the key point is change of flux.
Change of flux. Okay. Either anyone besides your friend's answer. They have one more you can also use for your inductance. Their answer I accepted. They have one more. It's related to your magnetic field. Anyone? Is it inductance? We also can define it as an energy store in a magnetic field. Okay, all right. So those give me the answers. Thank you for your answer. Okay, the next one. I just want to have a look on the next part here. Okay, the unit, the last one, the basic one, the simple one I asked. Okay, what's the unit for the inductance?
Henry.
Yes, Henry. Okay, all right. So I think I don't want to drag the time right now. So before I leave you all, let me take the attendance. Okay, today I just asked the simple one. Usually your class will be active, but today it looks like a passive. Okay. Always I get the response very fast. Okay, so your attendance is taken. You may leave the class right now. We'll see you in the next class on Friday. Could be a discussions class. At the same time, we'll have a calculations. At the same time, I need a feedback from you. We're going to do a task on the spot. Okay, so for today's class, we stop here.
Thank you, Miss. Have a nice
Okay.
day.
Thank you, miss.
All right.